Is it a coincidence that the derivative of the area formula of a circle with respect to its radius is exactly the circumference formula, 2 pi r? Nope, it is not a coincidence. Let's see why this makes sense. First, what is a derivative? A derivative is the rate of change. Kind of like with slope where we have change in y over change in x, the definition of a derivative has change in y over change in x, except the change in x is going to be really small, very close to 0. So when we plug in pi r squared over here, we get that the derivative is 2 pi r, or the circumference formula for a circle. What we are going to do is we are going to increase the radius by a really small amount, very close to 0, and let's call it dr, and we are going to see how this affects the area of a circle. Now the new area being added is this outer layer right here, and when we unravel that outer layer, we get a rectangle with side lengths dr and 2 pi r. Technically, the bottom side is 2 pi times r plus dr, but remember, dr is very close to 0, so let's just use 2 pi r. Now the new area being added is the area of this rectangle. So base times height is right here, 2 pi r times dr. Dividing both sides by dr, we get that the derivative of the area with respect to its radius is 2 pi r, which is the circumference of a circle. So a tactile way of thinking about this is with Hubba Bubba Bubble Tape. Whenever we increase the area of a circle, we are just adding more layers, which directly relates to the circumference of a circle. So you might be thinking two things right now. You might have noticed that the derivative of the volume formula for a sphere is exactly the surface area formula. And I would think that this is the same approach where we just think about increasing by the surface area. And you might be thinking, well, it doesn't work for a square because the square's area formula is s squared, but the perimeter is not 2s. And that is going to be for another video.